The shape of the tree is gradually becoming clear, but what of its timescale? In paleontological work, the time coordinate is provided by the extensive geological and geochemical investigations that allow the age of a given rock formation to be estimated. If a fossil is found in terrain believed by geologists to be 200 million years old, we know that the organism left their remains lived 200 million years ago, give or take a few million years. For molecular trees, the unit of measure is not time but number of mutations, the changes transmissible from generation to generation that the molecules have undergone in the course of evolution, or more accurately, the number of mutations compatible with survival and proliferation, the tolerable mutations, since other changes are eliminated by natural selection and leave no trace in extant molecules. In order to convert this unit into units of time, we must know the tolerable mutation rate. The time scale of a given tree will be very different if tolerable mutations are taken to occur on average every 1 million, 2 million, or 10 million years. This is one of the major uncertainties of the molecular method. The best way to resolve the problem is to compare the molecular trees with the paleontological trees. This works for the upper part of the tree, for which paleontological data is available. But what about the lower part? The answer has come just in recent decades from bacterial fossils. Bacteria are small entities, usually no more than a few 100,000th of an inch in size, with shapes ranging from globular to thread-like, visible only with a good microscope. There are plenty of bacteria in the world today. For most of us, the name bacteria raises specters of plague, cholera, tuberculosis, leprosy, diphtheria, and other dreaded ills. However, disease-causing microbes are only a small minority among a wide diversity of harmless or useful forms, which occupy almost every possible kind of habitat, from the balmy shelter of the human gut to the brine of drying seas and the boiling waters of volcanic springs. The richest source of bacteria is the soil, where these invisible organisms accomplish the all-important decomposition of dead plants and animals, recycling the constituents of life. Bacteria are the simplest forms of life, as and as we long suspected and now know, the earliest ones. Fossil traces of the organisms would therefore be invaluable in reconstructing and taming the lower part of the tree of life. Such traces have been found in the last decades. They are of two very different dimensions. At the visible level, the evidence comes from special layered rock called stromatolite. Such formations are derived by fossilization from huge bacterial colonies composed of superimposed mats, each consisting of a different kind of bacterial species. The top layer of the colony are made of organisms termed phototrophic that use the energy of sunlight to make their own constituents. Later, after they die, the substance provides food for the underlying layers. Colonies of this sort cover large areas in certain coastal regions, for example, in Baja California in northwest Mexico. With time, the colonies fossilize into stromatolites by a process of which every stage is known from certain representative rocks. Stromatolites have been found in diverse terrains in many different parts of the world, spanning all geological ages. Some date back to as much as 3.5 billion years ago, which for all practical purposes represent the limit of the useful geological record. It is possible that stromatolite generating colonies existed even before that time, but their traces could not have survived geological transformations. The second type of evidence of early bacterial life is microscopic. Most bacteria are enclosed within a solid shell or wall. This has allowed ancient bacteria to leave their imprints in mud, which later solidified into rocks, just as long extinct ferns have left their delicate tracings, ex- except that elaborate techniques and a healthy dose of critical discrimination are needed to identify a genuine bacterial microfossil and distinguish it from spurious traces and recent contaminants. A number of authentic imprints are now known. Interestingly, these traces are often found in stromatolites, providing additional proof, if any were needed, of the bacterial origin of these rocks. A few microfossils also date as far back as 3.5 billion years ago. So if life is at least 3.5 billion years old. Such is the startling message delivered by stromatolites and microfossils. Compare this age with the limit of about 600 million years beyond, with which virtually no trace of plant and animal has been found, and you can appreciate the enormous size of the hidden lower part of the tree of life, 4 to 5 times the size of the upper part, which encompasses the entire evolutionary history of plants and animals. During the immensely long time, almost 3 billion years, that preceded the emergence of the first plants and animals known to us by their fossils, life seems to have remained almost at a standstill. Stromatolites and microfossils do not look very different whether 1 billion or 3 billion years old. This appearance of stagnation is misleading, though. Events of cardinal importance took place in the shadow of the stromatolites, preparing the great explosion of life forms that burst forth around 600 million years ago. Oh my god. Yeah. According to the fossil traces, the bacteria that lived 3.5 billion years ago were diverse and advanced. They may even have included representatives of the most elaborate forms of phototrophic organisms known today. No doubt these early life forms were preceded by more rudimentary ones, themselves preceded by the common ancestor of life. When did this ancestral organism arise? Perhaps as early as 3.8 billion years ago, as suggested by physical analysis of fossil carbon deposits, kerogen, dating back to that time. These deposits show an enrichment in carbon atoms with atomic mass 12, that is, with a mass equal to 12 times the mass of a hydrogen atom, over carbon atoms with atomic mass 13. Such enrichment of the lighter over the heavier carbon isotope is a characteristic feature of a biological carbon assimilation. An upper limit of 4 billion years ago for the earliest life form is set by the conditions that probably obtained on Earth in the beginning of its history. Experts tell us that the Earth first condensed from a cloud of gas and dust some 4.5 billion years ago. For the next 500 million years, the young planet, battered by falling asteroids and racked by violent volcanic eruptions, remained unfit for life. The common ancestor of life probably appeared on Earth sometime between 4 and 3.8 billion years ago. Recognizing that these dates are uncertain, we shall adopt them as the most reasonable estimates available from the present state of our knowledge.